Well, we're back again at the physics video lecture. This is Physics 107B video lecture 22. Great topic today, radiation reaction. And we'll see if we get through it. So let's start off with radiation reaction. What that is. So we ended with the Larmor formula, which gave the power radiated by an accelerating charge. Well, let's start with that. So power radiated by an accelerated charge and it's proportional to the acceleration squared, so we'll put this down here. Power formula, mu naught q squared a squared divided by 6 times pi times c. And I'll give another relativistic formula. This is the one we're going to use. So for velocities much less than the speed of light, I'll just put this as a parenthetic note, since I have it right here. We'll just call it the star limiting case of P equals mu naught q squared, that's your numerator there, gamma to the 6th, which we'll learn about in the next chapter, 6 pi c a squared minus v cross a magnitude divided by c, this whole thing squared, and this gamma 1 over root 1 minus v squared over c squared. So we're going to get to know this expression in the next chapter, and the limit you can see as v is much less than c, then this gamma just turns into 1, and v is much less than c, so that this thing is much less than the a squared. So you get this expression back again, which is in fact the one we're going to use. So we'll put a box around it. This is the one we're going to use, and this is the one we derived in the previous hour. Good. So the idea now is that if a charge, an accelerated charge, if an accelerated charge is radiating power, then there must be a force on it, just based on Newton's third law. So you get the idea of a recoil force. So the radiation reaction force, or the recoil force, and we're just going to call it radiation. Just as a definition, radiation reaction force, okay? So to speak, in the opposite direction. If it's radiating in one direction, recoil force, so I'll even write here recoil, just to make sure we see what's going on there. And then what we're going to have is this dotted into the velocity is equal to, right, this is going to be a scalar, and that's power, right? Force dotted into velocity, force times dx over dt, work per time, so power, it's going to be the negative of this, simply because it has to oppose the direction of motion. If this were positive, it would be immediately a runaway situation. Okay. So this here, double star, by energy conservation. Okay. Now there are some important points here. We can only use this expression, strictly speaking, for motion that is motion that's restricted to some small area of space. Because if this, because remember the radiation concept is what goes out to infinity. Okay, so we have to have this localized in space in order to use the radiation concept. Otherwise, there's just energy in the field somewhere. But this is the stuff that goes out to infinity. So for that reason, this is going to be localized. Localized charge. And what we do is formally we just let the charge do some kind of motion where it returns to its origin periodically or not periodically. Okay. So what we can do is let charge return to its initial state. Return. To its initial state. So oscillatory periodic type of motion. And then again, that requirement is based on the actual definition and concept of radiation, which is what makes it out to infinity. Right? So the charge can't run away to infinity either. Okay? So it has to be localized. Good, so under those assumptions, we can go ahead and integrate the left side. So we'll integrate the integral f dot v dt, say from t1 to t2, and that will be the minus mu naught q squared. Those are all 6 pi c, but the a squared we'll have as a dv dt dotted into itself. Also t1 to t2. So we'll do an integration by parts on this expression here. So we'll have the mu naught q squared 6 pi c. And for our integration by parts, we have v dotted into dv dt, t1 to t2, minus v dotted into the derivative of dv dt. So v dotted into d squared v dt squared over time, t1 to t2. So this returning to the initial state allows us to eliminate this boundary term here. Okay. The initial state, therefore we can let that equal 0. And we'll bring everything under one integral now because we have a common v here. Okay. And I had a minus here, so I have a minus times minus is plus, close parentheses. Good, so what does that give us? We're going to have integral f radiation, And we'll bring this over, we got minus minus plus, so we'll have a minus mu naught q squared 6 pi c. So we have that v there. Here we'll have, I'll go ahead and write it with 2 dots. Equals 0. T1 to T2, where it's something where we return back to that initial state. So the state is v at T1 is equal to v at T2. And good, so we have an integral that's equal to 0. Now, strictly speaking, we can't just declare this expression in parentheses equal to 0, but that's what we do. Okay. So let's require that this equals 0. It's not quite an argument like a variational principle where this is absolutely arbitrary. This isn't actually absolutely arbitrary. But we're going to require this to be equal to 0, and we'll have an equation for the radiation reaction force. And that's going to be mu naught q squared 6 pi c times dA dt, right? That's the second derivative of velocity, so it's the first derivative of the acceleration, dA dt. And that is the Abraham-Lorentz equation. We're going to work with this for a bit. Abraham-Lorentz. Abraham and Lorentz. Okay. Yeah, okay, so Abraham-Lorentz formula. So this is the point where we run into seemingly paradoxical results, and I'll point them out. We're doing a couple problems on that. We shouldn't worry too much about the paradox, so that's not where the significance of this is actually to be found. Okay, that's squared. But yeah, what we're next going to do is just integrate this thing. So we've got Abraham-Lorentz formula. The radiation reaction force is proportional to the derivative of the acceleration. So our next step is to just take Newton's law. Mass times acceleration is equal to this constant times the derivative of the acceleration, and we solve that. So next, solve mass times acceleration equals mu naught q squared over 6 pi c dA dt. What we're after here is really we're just going to extract what's apparently present there as a time scale. Okay, so we're going to extract a time scale that's important. So let's do that next. So what we're doing is solving, because of course the highest derivative is on the left side here. So dA dt is equal to 6 pi cm divided by mu naught q squared times a. We'll just take it in one dimension, and we immediately have an exponential. Okay. So a is equal to, so I'll just write a of t is equal to e to the a0 e to the t divided by tau, where this is just going to be our time scale. Okay, right, first derivative, that's just a generic solution to the differential equation. So 1 over tau is equal to this, so tau is that inverse, is equal to u naught q squared 6 pi c amp. Okay, so now that we've found that, yeah. Okay, let's put a box around that. So this is not physically realistic behavior because it's actually a runaway exponential, but the time scale is going to play a role. Okay, and if this is not physically realistic, what happened here? Well, we're not looking at a situation where our system returns to its initial state. Okay. So yeah, the significance of this is primarily in the time scale that we're extracting here, and also we have to be careful with the whole subject. Okay, so time scale. Runaway. Okay, so not that physical. Now, what we're going to do, though, we've found this time scale. We're going to consider a situation that is very physical. Namely, suppose we have a charge mass on a spring, and we'll just talk about an oscillator. Right there, it's restricted from located. It's oscillating back and forth. It satisfies everything that we needed for the Abraham-Lorentz formula. And this analysis actually leads to some good result. Okay, anything there? Okay. Yeah, make a note there about how physical this scenario actually was. This next one is more physical. So this time, let's consider oscillating charged mass. So now we're back in our harmonic oscillator days. Okay, we've got spring constant, we've got a mass here that also has a charge on it. It's going to oscillate back and forth. There's our x-axis. But since it's an accelerated charge oscillating back and forth, we've studied in the last chapter, it's going to radiate. It's going to radiate power, radiate energy away, and we have a formula for that. And what we're going to do is include that radiated power as our damping force, okay, as our friction force, so to speak. So let's see, let's formulate that as we've done before. Right, we have the minus kx. So instead of our 2 gamma x dot, which is how we just treat the damped oscillator, we're going to put our radiation damping force right there in place of this thing here. Okay, so this is not that. And then plus a driving force. So the way we've treated this in the past is with a driving force and this 2 gamma x dot. Or actually, that's premature. Before we divided by m, this would have just been some constant times x dot like that. So that's what we're going to substitute in. And now, this equation looks like follows. Mx second derivative equals minus m omega naught squared, what's the k, x plus m u naught q squared over 6 pi c, x third derivative, plus the driving force. So that looks a little bit different than what we've had in the past. Okay. Am I missing a mass up there? No, we're good. 6 by C. Okay. So where's our time scale? U naught q squared 6 pi C m go like that. That's better. Yes. So this I can write as m times tau times x third derivative. Okay. So we're going to see this as a damping force as follows. Now suppose, since it's a driven oscillation, we settle into our the transient goes away, system settles into long-term behavior. Transient's gone, and we have x of t is equal to a cosine omega t plus some phase delta. Okay. Then what we have here is m times tau 3 derivatives. We just bring a minus omega cubed out right here. So x third derivative is just going to be omega cubed minus omega cubed x, or we could say it's minus omega squared x dot and that's actually the point we want right here. So it's a minus omega squared x dot, and when we plug it in here, we have m tau, we have a minus m tau omega squared x dot. So let's rewrite the whole thing. What do we have? Mx second derivative equals minus m omega naught squared x minus m tau omega squared x dot plus F driving force. I'll divide the whole thing by m just to put it into the form where you're accustomed to looking at it. X second derivative plus omega naught squared x plus 2 gamma x dot equals driving force over m. And now, you know, yeah, not the gamma that we would have talked about right here, right? This is the one that's due to our radiation damping force. With 2 gamma is equal to tau omega squared, cancel the m, right? 2 gamma tau omega squared equals mu naught q squared, once again, 6 pi cm omega squared. So here we can actually stop and remind ourselves what we learned with the damped driven oscillations back when we were studying that. We had resonance curves in which the resonance behavior was in that amplitude function. And for weak damping, we would have a sharp peak. We'll come back to the idea that this has to refer to a weak damping. So I'll just put here, recall damp-driven oscillations. Resonance, etc. And that's our damping constant, gamma. So yeah, you'll remember, to get any kind of peak behavior like amplitude as a function of omega, you were looking at that kind of situation for the case that this gamma was small. Small compared to the driving force, small compared to the force constant of the system. So that the damping would be small for any individual oscillation. The transient would be small damping. Okay, let's see, is there anything else to say about that? So, clock. Okay, good. So yeah, that's really the significance of this thing, that runaway dynamics isn't really what we've run into in nature, but this would be the actual radiation damping of this oscillating system. It's oscillating back and forth, driving away power, and of course, because it has a driving force, that's where the energy is coming from, right? This thing is doing the work. And this just fits the formalism of the damped and driven oscillator. So we're not really specifying, it's not necessarily on a spring, it would just be bound with a linear force law, a linear restoring force, with an external force that's driving it. Okay, so the next topic here, this is something I have out of Landau and Lifshitz. It's using the Abraham-Lorentz formula to get some feeling on the limits of validity for classical electrodynamics. So it'll actually kind of pick up on this discussion right here. So let me write that down. Using let's call this using Abraham-Lorentz. So using the Abraham-Lorentz formula, to determine the limits of validity for classical electromagnetism. equal E and M. So that's our next topic here. Let's see how we can tackle this. Okay, so we're looking for the limits of validity. And so we're going to do a consistency criterion. So that's what we mean by limits of validity. So begin with the equations of motion. So we'll have the classical equation of motion, and for a charged particle, m d dot, mass times acceleration, qe plus q v cross b. Right? That's the force on a charged particle. And then we're going to include the radiation reaction force. And so we'll include that on the right side. F radiation reaction u naught q squared 6 pi c v second derivative. So what we do is we include it on the right side as an added force that we didn't know about before. Okay, so it's added to the right side, but we're going to require that it remains small compared to these two primary contributions. That damping force that's small, just as we, on these kind of damping problems, we're looking at a small damping term, okay, for the classic, say, resonance curves. In the case of the damping here, the small damping constant allows us to treat the system as an oscillation with a small added force to it. So that's the spirit in which we're doing this here. So we write this whole thing down. So we'll just rewrite it. M v dot equals QE plus Q v cross B plus U naught Q squared 6 pi C B, two derivatives. Yeah, I better make sure I didn't even write that down. Requiring that F radiation be small, and when we say small, it's small compared to these two forces. Speaking of that driven oscillator, this could be your driving force. In other words, this could not only be your driving force, this could be your driving force plus your restoring force. So your restoring force, it would be a static part of QE, and then your driving force would be a time-dependent force, okay? So the scenario we had up here would be covered by what we're talking about here, okay? Good, so we have that with that stipulation. Now, we're just going to take another time derivative. So MV2 derivatives, QE dot plus QV dot cross B plus QV cross B dot, this product rule, plus U naught Q squared 6 pi CV3 derivatives. And what we're going to do, because we're looking for some estimates and some self-consistency checks, we're going to take a point in time in which V is equal to 0. Okay. So now choose a point at which V equals 0. See, as long as we're thinking about our oscillating systems, no problem at all, right? The thing is, twice per oscillation, it comes to a stop. So we'll take a point at which V is equal to 0 so we can estimate some of these quantities here. This equation, I should name these equations here because I'm going to make use of both of them a couple times. So when V is equal to 0, you see we get rid of this term here. Okay. And by assumption, this one is small. So at a point at which V is equal to 0, we can have an approximation here. And the second derivative approximately QE dot plus QE dot cross B. And then under the same assumption, MV dot is equal to QE. So I'll continue here, and MV dot is approximately equal to just QE. Okay. Yeah. So we'll put that in there. Okay. So we're ignoring this one for the moment. Okay. QE is the major contributor, and we can go back into this equation right here. So take this into equation 2 again, and we have, and divide by M, B second derivative Q over ME dot. But then we'll replace the V dot by Q over ME. Replace the V dot by Q over ME, so we have plus Q over M and another Q over M, so we square it, and we have E cross B. So now we're really looking at magnitudes of what's going on here, not the exact solution. Okay, so magnitude-wise, that's what we have. And now we can get the radiation damping force because it's proportional to V second derivative. So now, F radiation damping is just proportional to this, so we'll multiply out mu naught Q squared 6 pi C times these two terms here. So the first one we're going to have Q over M, E dot, and for the second one we're going to have, in fact, let me simplify this right now. So I have the Q squared, so I'll have Q to the third, 6 pi C M E dot, and for my magnetic term I've got the Q over M squared, so I have mu naught Q to the fourth, okay, 6 pi C M squared, okay, Q over M to the power, and then E cross B. So again, I'm really looking at this primarily for the magnitude of these quantities here. So this is our damping force. We're still primarily, or we're going to use oscillating charges because they really fulfill all the requirements. So for an oscillating charge, that's the next thing. We can replace the E dot by omega E, right? It's just oscillating with omega. E dot is omega E. And for the magnitude of the radiative force, of the reaction force, so for the magnitude, we'll drop the equal sign. We've got mu naught Q to the third omega E over 6 pi C M. And we've got mu naught Q to the fourth EB over 6 pi C M squared. So let's put a box around that. These are what we're going to work with now. So once again, the consistency is we're requiring that the radiative force actually be much smaller than say the driving force. Okay, so what conclusions can we draw here? So we've assumed, for example, that this is much smaller than the electric force Q times E. And much smaller than QV cross B as well. Let me send this up. See what's going to happen here. So we had assumed that this radiative force is much less than the driving force. Okay? And we have a QE in here. Okay? So from this thing directly, we get mu naught Q to the third omega E 6 pi C M much less than Q times E, and we can cancel one of the E's and one of the Q's. So we end up with, so that mu naught Q squared omega 6 pi Cm much less than 1. yeah, by the way, omega, you know, this is dimensionless, so this of course is our tau, right? So this is that omega times tau is much less than 1. So we can continue with that idea. So, and since omega equal to c times k, c times 2 pi over lambda, we can express this in terms of a length. So yeah, let's go ahead and put that in there. We get mu naught q squared c 2 pi 6 pi c m lambda, much less than 1. And we're not done with this. Yeah, the unit integers, that was a implication. So what do we have here? When the c cancels, we have mu naught q squared. 2 pi over 6 pi will have 3 c cancels, 3 m lambda, much less than 1. So there's a wavelength that has to be much greater than this mu naught q squared over 3m. Okay, now this we're going to put into relation. I skipped something here. This is true. Okay, lambda. Yes. Okay, I'm going to drop the 3. We're not worried about the 3 here. But since mu naught epsilon naught is equal to 1 over c squared, we have one more relation here. Lambda has to be much greater than, so that we end up with q squared. I'm going to ignore the 3, okay, because it's just it's there, but it's a small quantity. Okay, q squared, the mu naught, 1 over epsilon naught, c squared, so over epsilon naught mc squared. So either way, this is identical. Yeah, we leave the 3 in there just so we don't argue away. So what we're saying is the wavelength of our radiation has to be much greater than this interesting quantity here. The 3 doesn't really concern us. The q squared over epsilon naught times mc squared. So there's a limit on how small the wavelength can be, and classical electrodynamics still be consistent. Right? Again, the consistency was we're having the radiation damping be sufficiently small. But this expression here has a bit more meaning. We'll return to it, and then we'll summarize all these things. So this is one of the criteria. We have wavelength criteria. classically, the wavelength can't just be arbitrarily small. So if this is a wave, this is a wavelength because it came from our omega, then we're talking about a quantity here is also a length scale. So what's the meaning of the length scale right here? I'll just give it a name. The meaning of R equals, because it's a length, Q squared over epsilon naught MC squared. Like I said, the 3's irrelevant. Now we also have the similar thing to be said about this term here. So we also have U naught Q to the 4th EB 6 pi C M squared is supposed to be much less than Q times E. Right? Because this is part of the damping force, this is the original force. So again, we can get that cancellation and we'll get a criterion for B. And we'll just, this one we'll just solve for. I don't think we're gonna. So B much less than 6 pi C M squared over mu naught Q to the 3rd. Much less than, okay. And this can be reformulated by the same arguments we had up here as epsilon naught over C M squared C to the 4th over Q to the 3rd. So the magnetic fields can also not be too large. Okay. Again, this is in order that we have consistency. So we have two criteria, magnetic fields and the wavelengths. And the last thing we're going to do is look at this thing again. We've actually seen part of this. We've seen it in a different form. In fact, let me consult the clock. Yeah, this is perfect. And then I'll summarize them. So we have these two criteria. Wavelengths have to be, of the radiation, have to be much greater than this expression here, and magnetic fields have to be much smaller than this quantity right here. So what is the meaning of this expression right here? Since we've actually dealt with something similar, there's something old in there and something new. So we have that length scale. Let's rewrite this equation star right here as MC squared is equal to Q squared over epsilon naught R. Okay. What we recognize this as is basically the energy of a very small charge distribution. Okay. I think we integrated something up, I think for a spherical charge, Q, spherically symmetric and uniform, we had an expression like this maybe with 3/16 or something earlier in the semester. So up to those constants, this is the energy a spherical charge distribution, a spherical uniform charge of radius r. And this is a relativistic energy expression that we're actually going to derive and discuss in the next chapter on relativity. So I'll just write here relativistic energy. So if you take this m, say the mass of an electron, mass of an electron, charge of an electron, then you would have a classical radius of an electron. And you guys should actually plug these numbers in and see what you get. Okay, that's interesting. So that criterion for the wavelength, remember, it had to be much greater than this very small quantity here. So this is the idea that if you took all of the energy of that charge distribution, the electromagnetic energy, and if you equated it to the mass energy, relativistic mass energy relation. So yeah, those are the criteria. And this is, right, if the wavelength is much smaller than this, or if it's not much larger than this quantity here, then classical electrodynamics breaks down. So let me summarize those, put them all on one place here. Summarizing. Classical E&M. Wavelengths, lambda, has to be much greater than Q squared epsilon naught MC squared. Fields have to be much less than epsilon naught over C M squared C to the fourth. Now you see there's an energy there over Q to the third power. And you can say it would break down when the lambda approaches this quantity, when the field is this strong. Okay. Yeah, and with this, the meaning of this length scale here, having been given by this idea here, that's where what the meaning of this length scale is. Q squared over epsilon naught MC squared. Good. So yeah, the final note there is that you'd say that theory would break down if the wavelengths were on the order of this, and if the fields were, on the order of this strength. So we want the wavelengths to be much greater, the fields to be much less than these quantities here. Okay, good. We'll leave it at that. Perfect way to segue into relativity theory, where this MC squared expression, it's clearly an energy, will play a big role. And also I had earlier in the hour mentioned velocity is much less than the speed of light. That's also going to play a big role. Good, see you then.